This week, we continue on with our observations of stream morphology and how it creates the physical habitat for stream organisms. We want to take a look at the bank-to-bank shape of the stream channel, its cross-sectional form, and think about how that aspect of the stream relates to the in-stream flow of water and how, at times of high flows, or even flood flows, the stream ecosystem connects with its floodplain. As you know, stream flow is a dynamic quantity, varying sometimes dramatically as a result of the amount and timing of runoff arriving in the river. As the amount of water being transported by the river increases, the river's stage, or the height of the water in the channel, rises. So, what observations do we make in the field that can allow us to determine the current stream flow and make estimates of the capacity of the channel to carry water before it floods? Our practice is to make a series of measurements that are perpendicular to the flow of water in the stream channel and combine those with measurements of depth at regular intervals so that we can develop a rough plot of the cross-sectional shape and area of the stream channel. Here we are stretching a tape across what is referred to as the wetted channel width. This is a measurement that will vary depending on how much water is flowing in the stream during your fieldwork. Once the wetted channel width has been determined, you want to break that distance into regular intervals and measure the depth at each of those intervals. Using that set of XY data, we can sketch the shape of the cross-section and use a basic geometrical formula to approximate the cross-sectional area of the stream. If we used a velocity meter, or we did the old school method of timing how long it takes a float to travel a certain distance, we can combine our estimate of the cross-sectional area with a measurement of the stream velocity to come up with a value for the current stream flow. We'll take a break to work with some data, and then we'll return to this video to see how bank full flows are estimated and how a couple of other key characteristics of the stream channel are derived. Okay, we're back. As mentioned earlier, we note that as stream flow increases, the stream stage, or the height of the water above the stream bed, also increases. Under normal regime conditions, what is known as bank full flow occurs approximately every 1.5 to 2 years. And I hope you recall calculating recurrence intervals and evaluating graphs of exceedance probability. Bank full flow is the maximum amount of water that can be contained in the stream channel before spilling out into the floodplain. But if such channel shaping flows are relatively infrequent, how can we get a sense of what bank full flow is if it's hard to observe it directly? At that max Q, the stream also has the maximum amount of power to do work eroding and transporting material, and that work leaves some obvious signs of bank full flow, like cut banks, where there are obvious changes in slope and texture of material, and the exposed roots of riparian vegetation. Also, other more subtle indicators of bank full stage, like changes in the type of vegetation that can grow below the bank full line, staining, mud deposits, and moss growth on bankside boulders, and changes in the size of sediment deposited on point bars and breaks in the deposit of leaf litter. Once we've identified some strong bank full flow indicators at our field site, we can progress to the next phase of characterizing the stream's physical habitat using a procedure that is the same as we used to develop our cross-sectional area for estimating stream flow. We measure the width of the stream at the bank full stage, and we also measure the maximum depth of the stream when the flow is at that level. We then double that depth and use that so-called flood-prone elevation to gather the last bit of data needed for this part of the channel type classification. In a complete data collection exercise, we would also gather data at regular intervals across the bank full width to generate the shape of the cross-section.
Alright, so what do you want to be? You want to be the beholder here or the walker?
Yeah, I'll just hold it.
Okay. Second, try to control the...
Using the flood-prone elevation, recall that is 2 times the bank full depth. The field workers stretch a tape measure level to that elevation outwards from the stream channel until that level line intersects another change in the slope of the stream's valley. The total width at that point is known as the flood-prone width and is a measurement of how much of the upland terrestrial environment is a part of the river's riparian zone. In other words, how much hydrological connectivity does the stream have with the landscape that surrounds it? Using the measurements of the flood-prone width and the bank-full width, we can calculate a value known as the entrenchment ratio for the stream, which is the final part of this phase of our channel type classification for this week.